This unit is finished. Now we will see the questions which have appeared in GATE recently. And from the next lecture, we are going to cover MOS capacitor. First, try these questions yourself. There are total 2 questions and total time provided is 4 minutes and 30 seconds. Your time starts now. Time is up. Now we will see the solutions. Which of the following statements are true for a BJT with respect to its DC current gain, particularly common emitter current gain. Under high level injection condition, in forward active mode, common emitter current gain will decrease with increase in the magnitude of collector current. This point is true. Under low level injection condition in forward active mode, where the current at the emitter base junction is dominated by recombination generation process, common emitter current gain will decrease with increase in the magnitude of collector current. This is false. And this line here is just a characteristic of low level injection. Common emitter current gain will be lower when the BJT is in saturation region compared to when it is in active region. This is true as we get the best values of all the current gain parameters in active region, and that is the reason why BJT are used in active region for amplification processes. A higher value of common emitter current gain will lead to a lower value of the collector to emitter breakdown voltage. This is also true. We have covered this topic in non-ideal effects in the avalanche breakdown. The theory for all these points is already covered in the previous lectures, and you have to go through the short notes also, which are provided in the video's description. Now we see the second question. We already know that common emitter current gain is equal to collector current divided by base current. We can simply write common emitter current gain is inversely proportional to base current. From the Gamal-Pun model, we know the current density through the base is equal to negative of magnitude of charge on an electron into diffusion constant of minority charge carriers into square of intrinsic carrier concentration multiplied by exponential of base to emitter voltage divided by thermal voltage, the whole expression being divided by integral of whole concentration with respect to distance across the base width. You should know that this expression here is actually the whole carrier concentration, but since it is written clearly in the question that the whole density profile is same as that of doping, therefore we can change the whole carrier concentration with doping concentration. This statement in the question is simply a way of telling you to consider low level injection in BJT. The current through the base is simply the multiplication of current density into area. For current, we can simply write that current through the base is inversely proportional to integral of doping concentration in the base. Now, let this equation be the first equation and this equation to be the second equation. From these two equations, we can conclude common emitter current gain is directly proportional to the integral of doping concentration in the base across the base width. Therefore, we can have the ratio in the form if you have even a small knowledge of integrals, then you might know that integral is actually the area under the curve. For example, if you have any curve and we have to integrate with respect to x, then the integral is actually the area under this curve. So, you have two ways to solve this problem. One is you can divide this concentration profile into a triangle and rectangle, or you can directly find the area if you remember the formula of area of trapezium. The other way, which is quite lengthy, is that you can find the equation of this line and then integrate it manually. However, I am going to do the easiest way, which is finding the area of triangle and rectangle. The doping of another base has uniform concentration profile, so it is also a rectangle. We know the area of triangle is equal to 1 upon 2 into base into height. Base is base width and height is 10 raised to the power 17 minus 10 raised to the power 14. Area of rectangle is equal to length into width, which is base width multiplied by 10 raised to the power 14. In the second case, area of rectangle will be equal to length into width. Length is base width and width is equal to 10 raised to the power 17. We can cancel the base width. This is going to be the exact expression, but you can see in the options that the options are provided in terms of approximation. Therefore, we can ignore 10 raised to the power 14 as it is significantly smaller than 10 raised to the power 17. After ignoring 10 raised to the power 14, we can cancel 10 raised to the power 17, which will finally give the common emitter current gain of transistor 1 to be equal to 1 upon 2 times the common emitter current gain of transistor 2. Originally, gate authorities published this answer, but this question was challenged by various candidates. In this subject, there is a big problem. In standard textbooks, many times statements are made considering only one topic while ignoring the other topics completely to avoid confusion. Similarly, if you consider only recombination process, then you may find the statement increase in the base concentration results in more recombination in the base, which leads to decrease in current gain. But this statement cannot be easily converted into mathematical relation. See these three examples. For all these three cases, we can say the common emitter current gain will increase as the base doping increases. In electronic devices, temperature also plays a significant role. Like there is no single formula for band gap energy which is valid for all the temperatures. It deviates at very high and very low temperatures. Even the ideal diode current equation deviates at high and very low voltages. It may be possible that the three shown relations may be valid for different temperature ranges, but a simple and straight mathematical relation cannot be formed valid for all temperatures. That's why authors of standard textbooks usually avoid making mathematical relations. And in this question also, nothing is provided about temperature. The main problem is the question was based on Gummel-Poon model, but many students began to think other concepts like the one we just discussed. If the question have said directly that use Gummel-Poon model, then situation would change. But have you ever seen any question in which it is itself written what you are supposed to use? Obviously no. Due to this dilemma, the question was considered wrong and grace marks were provided to all the students. Short notes for this chapter are provided in the video's description, but still you should read books. You can find all the concept in the short notes, but still you may find few facts or data which you have to simply learn. Like consider this GRIT question which appeared in GATE 2025. This question is very simple. The answer is arsenic and phosphorus. But as you can see, there is no concept behind this point. Even if there is a concept, then you should be aware of that as you might have studied in chemistry in senior secondary school. For such type of points, you should refer to books.